Welcome to Ask and Learn.
We want to sketch the graph of y is equal to x cubed over x cubed plus 1. So we're given in this chapter this laundry list of steps we should follow in order to go about finding what the graph looks like. So let's just go ahead and start by following that list. So the first thing they tell us is to find our domain. So we just want to make sure where our function's denominator does not equal 0. So if you were to solve x cubed plus 1 is equal to 0, you'd get x is equal to negative 1. So we just need to exclude that point. So it's going to be negative infinity to negative 1 union negative 1 to infinity. The next thing they tell us is to find our intercepts. So let's go ahead and find the y-intercept first. So that's going to be where x is equal to 0. So we're going to get y is equal to 0 cubed over 0 cubed plus 1, which is just 0. So our origin will be our y-intercept. And then to find our x-intercepts, we set the function equal to 0. So get 0 is equal to x cubed over x cubed plus 1. And we know that nothing we ever plug into the denominator will make the function equal to 0. But if we set the numerator equal to 0, it will. So that just tells us x is equal to 0 will be our x-intercept. So the only intercept we'll have is our origin. All right, so now let's go ahead and look for our symmetry of the function. So rational functions aren't really known for being periodic. So let's go ahead and check to see if it's even or odd. So we can find symmetry about the y-axis or about the origin. All right, so here we can rewrite this as negative x cubed over negative x cubed plus 1. Now, if I were to distribute that negative in the numerator to the denominator, we're going to get x cubed over x cubed minus 1. So this here is neither f of x nor is it equal to negative f of x. And so due to that, we know we're going to have no symmetry, or at least no symmetry along the y-axis or about the origin. All right, next they tell us to look for asymptotes. So we know from chapter 2.6 that the end behavior of this will go to where we just divide the leading coefficients since they are the same degree. So the limit as x approaches positive or negative infinity of f of x is going to be, well, our leading coefficient numerator is 1 and the denominator is also 1. So we have a horizontal asymptote at y is equal to 1. Now we need to look for our behavior for our vertical asymptotes. So here, that would be where our denominator is equal to 0, which is going to be at x is equal to negative 1. So let's first look at negative 1 from the right of f of x. So we'll have negative 1 from the right cubed over negative 1 from the right cubed plus 1. Now a number slightly to the right of negative 1 is still going to be negative, and if we cube a negative number, it's going to be negative still. And then if we go and cube negative 1 again, it'll be slightly to the right, and it's still going to be smaller, or I guess larger than negative 1. So if we do 1 minus something larger than negative 1, well, that's going to be positive. So here, this is going to go to negative infinity. And we can use a nice little trick to make it so we don't have to go through that same process to find what happens to the left. So x cubed plus 1 is what I like to call cubic-like around the axis, or around the vertical asymptote. So since it's an odd degree, it should have opposite in behavior. So this here should be going to positive infinity to the left of x equal to negative 1. And you could go through the same steps, I just think that saves a little bit of time. All right, next, I'm going to combine the next two steps because I think they go together, and we want to find where our function is increasing and decreasing and determine any kind of local max or mins that may exist. So that means we need to find out what y prime is. So let's do that on another page. So we have y is equal to x cubed over x cubed plus 1. And to take the derivative of this, we're going to need a quotient rule. So the way I remember quotient rule is low d high minus high d low all over the square of what's below. And now we can go ahead and take the derivatives of x cubed, which is going to be power rule to give us 3x squared. And again, we'll get the same derivative for 3x cubed plus 1 since the derivative of 1 is just going to be 0. Now, if we do that little bit of algebra there, this here should simplify to 3x squared over x cubed plus 1 squared. All right. And now we can go ahead and set this equal to 0 to try to find our critical points. So we'd set the numerator equal to 0, and that would just tell us x is equal to 0. All right, so we're going to need to know that information. So y prime here is going to be 3x squared over x cubed plus 1 squared. Now this function will be increasing where y prime is strictly larger than 0. And I went ahead and already solved that off on the side. And actually, even looking at this, we know that our numerator will always be greater than or equal to 0, since it's x squared. And in the denominator, since we have that squared term there also, that will also be larger than or equal to 0. So we actually are increasing on our entire domain, or all of the intervals are increasing, I should say. So it's going to be negative infinity to negative 1, union negative 1 to 0, union 0 to infinity. And remember, we're just excluding 0 because our derivative is actually equal to 0 at that point. All right, and so for decreasing, we have nothing. So y prime less than 0, nowhere. So for x is equal to 0, it is increasing to the left and increasing to the right. So that tells us this here is a saddle point. Or in other words, we're going to have a change in concavity there. So we also already know one point of inflection for this. All right, now the next thing is we want to actually find the rest of our points of inflection and our concavity of the function. So we're going to need to know what y double prime is, so let's go ahead and solve for that. So we have y double prime is going to equal to, well, we're going to have to use quotient rule once again. So it's going to be x cubed plus 1 squared times the derivative of what's in the numerator, 3x squared, then minus them in the opposite order, so 3x squared times the derivative with respect to x of x cubed plus 1 squared all over x cubed plus 1. So before it was squared, so now it's going to be to the 4th power. So the derivative of 3x squared, we'll use power rule to take that derivative, so it'll be 6x. And to take the derivative of x cubed plus 1 squared, we're going to need to use power rule as well as chain rule. So first, using power rule, we get 2x cubed plus 1. And then taking the derivative of x cubed plus 1 will be 3x squared. All right, now simplifying all that algebra there, we should end up with negative 6x 2x cubed minus 1 all over x cubed plus 1 squared, cubed. Right. Now let's go ahead and set this equal to 0 so we can find our possible points of inflection. So that would tell us x is equal to 0, or 2x cubed minus 1 is equal to 0. And that would have where x is equal to the cubed root of 4 over 2. Right, so we have our two possible points of inflection now. So we at least already know x is equal to 0 is a point of inflection, but we also need to see if our other value is. And so first, let's just go ahead and say this value here is about 0.793. All right, so y double prime was equal to negative 6x times 2x cubed minus 1 all over x cubed plus 1 cubed. Now this function is going to be concave up when y double prime is strictly larger than 0. And that should give us negative infinity to negative 1 union 0 to the cube root of 4 over 2. And the function is going to be concave down when y double prime is strictly less than 0, which is going to be the interval negative 1 to 0 union cube root of 4 over 2 to infinity. So putting down our 2 points of possible inflection. So to the left of 0, the function is going to be concave down. To the right of 0, the function should be concave up. And to the right of cube root of 4 over 2, the function is going to be concave down. So we can see that all of these are points of inflection. Now this was the last thing they told us we should do before we actually start graphing. So let's go ahead and graph. So we had a intercept at only the origin. So we'll go ahead and put that down. We can go ahead and put our asymptotes down as well. So we know at y is equal to 1. Actually, let me go ahead and put that a little bit above. So at y is equal to 1, we will have a horizontal asymptote. And at x is equal to negative 1, we're going to have our vertical asymptote. And we know to the right of negative 1, we should be approaching negative infinity. And to the left of negative 1, we should be approaching positive infinity. So we have no maxes or mins, but we do have points of inflection at 0 and cube root of 4 over 2. So let's go ahead and plot that. So this here will be cube root of 3 over, or cube root of 4 over 2. And we know this should be a inflection point. So we went ahead and plotted everything. So let's go ahead and start to the left of -1 since we have no points of interest over there. That's just going to tell us that we will keep on going and get very close to our horizontal asymptote. And now to the right, well, we know we need to start from -infinity and keep on going until we hit our origin. And then there's going to be a change in concavity until we reach about the cube root of 4 over 2, and then it's going to change concavity again, like that. So actually, maybe let me try to draw that a little bit better for the change in concavity. So here it's changing concavity, and then it's going to stay like that until about here, and it's going to just keep on getting closer and closer. So maybe you can draw the concavity change at cube root of 4 over 2 a little bit better, but it should look something along those lines. Now you could go in and maybe say where that y value occurs, but for me, yeah, I don't think it matters too much since we're just trying to sketch the graph. So I would say this is all we really need to do, and we can stop here for the sketching of the graph.